Okay, we have here today another integral, but this is one for the Laplace transform playlist. We have the integral from 3 to infinity of cosine 4t times e to the minus 2t dt. And I want to thank Doron Esri for the suggestion for this. I already did this problem in another video that I believe I have in the Laplace transform playlist. And his suggestion is to use unit step functions on this. And it's interesting because it's like the methods are very parallel. If you do the u substitution, you can really see how it works with the unit step function. But for this one, I'm just going to use unit step functions on it in order to address the one problem we have. I can't just go ahead and use Laplace transforms on this. In the other video, I did a u substitution to clean up this bound. But the other way to do it is write it like this to set up our Laplace transform, but then multiply in unit step function at 3 and multiply it times everything else that we already have. And the reason this is going to work, we can just take a look real quick at the unit step function. This is going to be a very rough sketch because I don't even have my ruler ready, but the precision of it's not really going to matter because the unit step function, it's just going to look something like this. It's just going to be a straight line starting at a value. And for us here, if we're just looking at u t minus 3, this here will be our t-axis, then this point 3 is the cutoff. So then everything to the right here is going to have a value of 1, and then everything to the left is going to have a value of 0. So if you think of this integral as being some curve, we have no idea what it looks like from 0 to infinity, right? I don't know. It probably looks nothing like that, but whatever. What's going to happen though is because we've got the unit step function on, everything here is 0. So it actually just like zeroes out this part of our curve right here. And so by doing that, this here is going to be equivalent to our original problem. So then going ahead with this, what we have here is just going to be, we can write this as the Laplace transform of u t minus a times cosine of 4t, but we have to shift it by a. So this is going to be cosine, we can write it as 4 times t plus our a value is going to be 3. And sorry, I should actually write in, we know what this is. This right here should be a 3. And so then for this, we'll use our formula for a Laplace transform of the unit step function times some function t, which is going to be, where our f of t is going to be this right here. So what's going to happen, again, our a value is just 3. So using this, we're going to have e to the minus 3s. And then this part, we're going to need the Laplace transform, and I'm going to distribute it in. So it's going to be cosine 4t plus 12. But now for this Laplace transform, we're going to just need another formula because we've got this shifted. It's not, we can't just use the normal cosine function. If it was just 4t, we'd be fine, but we get this plus 12 to deal with. So let me make a little space for that. Okay, so now for this right here, we're going to use our formula over to the right. I derived this in a previous video. And also for the unit step function, any of this, if you need more on Laplace transforms, I'll provide a link to the whole playlist where we did this. But anyway, going ahead with this kind of complicated formula, the one nice thing about it is you'll notice the denominator is exactly the same as the cosine formula, so we can put that down. That's just going to be s squared. Here, like our a value is going to be 4, and our b value is going to be 12. So in the denominator, we end up with just squaring this, s squared plus 16. The numerator is going to become s cosine of b, which is 12, minus a value is 4 sine of 12. And so this will be our solution in terms of Laplace transform, but originally we had this integral we need to deal with. One thing I really failed to mention is I kind of totally glossed over the fact that I'm assuming that we have an s value in here. So it's really s equal to 2. So what I should have done earlier is wrote this in as st, so we really have a Laplace transform, but it's the same idea. So we did all the Laplace transform stuff on this, but in our original integral, we just have s equal to 2. So all we're going to need to do to finish this off is just plug 2 into this thing. So we're going to end up with e minus 6, plug it in here, 2 cosine 12 minus 4 sine of 12. Plug 2 in here, we're going to get 4 plus 16. This becomes 20. Just a little simplification. If I factor a 2 out of everything, then I can make this a 10, bring this into the denominator. So for my final solution of this, we just get cosine 12 minus 2 sine 12. Putting this stuff together, 10 e to the 6, and that's it. Okay, there you go. Interesting problem using the unit step function. Thanks everyone for watching. Have a good day.